Hi, welcome to our series on shortcuts and tricks for evaluating series in summation or sigma notation. In the first part, we covered introduction to sigma notation, properties of sigma notation and how they are applied in solving questions. And we also covered extensively the use of standard formulae in evaluating series that are written in sigma notation. In part 2, we would be covering arithmetic, geometric, and alternating finite series that are written in sigma notation, the shortcuts and tricks that are involved when you are dealing with them, and in particular how to look at the summand of the summation and recognize that you are dealing with arithmetic, geometric, or alternating finite series. And then in the video of part 3, which will be published soon, we'll be covering the use of the Morse theorem in evaluating series, as well as evaluation of partial sums of telescoping infinite series and the use of the method of difference, particularly to evaluate telescoping series that converge. So in the case of an arithmetic series, you will recognize that the sigma notation you are dealing with is an arithmetic series when the argument or the summand of your sigma notation is a linear function, a function of the form AR plus B, where the degree of R is 1. You know that you are dealing with an arithmetic series, and once that happens, you have two options. It's either you use standard formulae, because there is a standard formula for summation from R equals 1 to n of R, which you can apply and you'll be able to evaluate such a series. But the best practice is to write down the first term, the number of terms, and then the last term, and you can then use the formula for the sum of an arithmetic series to be able to get the answer quickly. So we recall that for an AP with first term U1 and common difference D, the general term or the nth term is given by un equals u1 plus n minus 1d, where n is the number of terms. But then it is good to write the formula or to master the formula in a general form, whereby the last term of your series, which is arithmetic, is the first term plus the number of terms minus 1 times the common difference. This form of the formula in particular is important because most of the time your last term or your general term will not be the nth term. There are cases where the sigma notation would be such that the lower limit is not 1. It could be 0 or it could be any other number. In that case, the last term would not be the nth term. Where the lower limit is 0, for instance, you would have n plus 1 terms, and so the last term would be un plus 1. So writing the formula might be confusing if you don't master this general form written in words. And the most important thing is that since the sigma notation deals with sum, we have to master the formula for the sum of the first n terms of an arithmetic series, which is given by the sum of the first n terms being equal to the number of terms over 2 into the first term plus the last term. That formula can also be written as n over 2 into 2u1 plus n minus 1d, and it is obtained simply by replacing the formula for the general term, which is the last term, in this other formula, and then we get this one. Again, it is important to write the formula in words rather than in symbols because of the explanation I've given up, in that you would not most of the time be dealing with the sum of the first n terms. It could rather instead be the sum of the first n plus 1 terms or any other number of terms for that arithmetic series, and you would have to be very careful in applying the formula. Now we proceed with examples. The first example says, given summation from r equals 1 to 60 of 2r plus 5, find the sum of the middle 20 terms. You can see that the question is tricky because our formula is talking about the sum of the first n terms, Now the question is asking us to find the sum of the middle 20 terms. The trick here is that the upper limit, in short, the number of terms, is 60, and 60 is divisible by 3. That implies that if you divide 60 by 3, you would have 20. So we have the first 20 terms, the middle 20 terms, and then the last 20 terms. So we would be interested in the sum of the middle 20 terms in that series. So actually the sum of the middle 20 terms is the sum of the first 40 terms minus the sum of the first 20 terms. Remember, if there are 60 terms, it means from the sum from the first term to the 20th would be in the first 20, while the sum of the terms from the 21st to the 40th would be in the middle 20. That is why to get the sum of the middle 20, you have to first find the sum of the first 40 terms, and then you subtract the sum of the first 20 terms to have the required sum. And from the formula of the sum of the first n terms of an arithmetic series, we need the number of terms, the first term and the last term. So we use the sigma notation then to evaluate the first term, which will be obtained when r equals 1. When you substitute r equals 1 in the summand, you get 2 into 1 plus 5, which gives u1 as 7. We also need the last term in the first 20 terms, which will be obtained by substituting r equals 20 in the summand to have 2 times 20 plus 5, which gives 45. We also need the last term in the first 40 terms, which will be obtained by substituting r equals 40 in the summand, which would give 2 into 40 plus 5, which gives 85. We then proceed to have the sum of the middle 20 terms, which is S40 minus S20, and the sum of the first 40 would be 40 over 2 into the first term plus the 40th term, minus the sum of the first 20, which is 20 over 2 into the first term plus the last term. When you proceed to evaluate, you get 40 over 2, which is 20, into the first term, which is 7, plus the last term, which is 85, minus 20 over 2, which is 10, into the first term, which is 7, plus the last term, which is 45. And from there, we have that the sum of the middle 20 terms is equal to 1,840 minus 520, giving 1,320. In the second example, we are asked to write the series in sigma notation, which is 3 plus 5 plus 7 plus the other terms plus 49. Actually, in order to write this series in sigma notation, we need the lower limit of the summation, we need the upper limit, and we also need the general formula of the series, which will serve as the summand. To begin then, we get the argument or the summand of the summation by finding the general term of this series, which happens to be arithmetic, because there is a common difference. Terms are obtained by adding 2 to the previous terms, and so we'll use the general formula for the nth term of an arithmetic series, which is ur equals a into r minus 1d. A, the first term, is 3 and the common difference is 2, so we get 3 plus 2 into r minus 1, which simplifies to give 2r plus 1. So that general formula for the nth term or the rth term of that series is ur equals 2r plus 1. So this becomes our summand in the sigma notation. Then we need to find the lower limit of our sigma notation, which is actually obtained by equating the summand to the first term. So ur equals 3, the first term. We'll then have that 2r plus 1 equals 3, giving r as 1. So the lower limit of our summation will be 1. Then we'll also need to find the upper limit, which will be obtained by equating the summand to the last term, which is 49. So we proceed to have ur equals 49, which gives 2r plus 1 equals 49. And upon solving for r, we have 24 as the upper limit. We can then write our series in sigma notation, which would be summation from r equals 1 to 24 of 2r plus 1. In the second example, we are required to evaluate summation from r equals 0 to 100 of 3r plus 2. Since the summand or the argument of the summation is a linear function, we can use standard formulae, or we apply directly the formula for the sum of an arithmetic series. Going by the first method, we would start by writing out the series so that we can read the first term and the last term. So summation from r equals 0 to 100 of 3r plus 2 is 2 plus 5 plus 8 up to 32. So our first term would be a equals 2 and the last term is 302, while the number of terms which we learned in the first part of the series, that you obtain the number of terms by taking the upper limit minus the lower limit and then plus 1. So 100 minus 0 would give 100. Then when you add 1, you have 101 terms in that series. We can then apply the formula for the sum of an arithmetic series, which specifies that you have to divide the number of terms by 2 and then multiply by the sum of the first term and the last term. So the number of terms in the series being 101, we divide by 2 into the first term, which is 2, plus the last term, which is 302, giving 15,352 as the value of that series. Now, in the alternative method, we can use the standard formula as I already specified. So to use standard formula, we have to be careful here because the standard formula are applied in the case where the lower limit is 1. And since we have the lower limit 0 and not 1 in this case, we have to be strategic in that we pull out the first term, which is obtained when r equals 0. So we'll get 3 into 0 plus 2 plus the sum of the terms now from the lower limit being 1 to the upper limit, which is 100 of 3r plus 2. So we'll get this result, summation from r equals 1 to 100 of 3r plus 2 plus 2, the first term obtained by substituting r equals 0. In this form now we can apply standard formula without any problems. Now, one of the properties we saw in the first part of our series is that the sigma notation is distributive over addition and subtraction. In the next step, we distribute the sigma notation into the summand to have 3 summation from r equals 1 to 100 of r plus summation from r equals 1 to 100 of 2 plus our first term that we pulled out, which is 2. And now we proceed to have 3 into summation from r equals 1 to 100 of r. The formula says n into n plus 1 over 2, and n being 100, we then have 3 into 100 into 100 plus 1 over 2 plus summation from r equals 1 to 100 of 2 simply means summing 2 from a count of 1 to a count of 100, and this means we are adding 2 100 times corresponding to the product of 102, and then plus the first term that we had pulled out, so that upon simplification we have 15,150 plus 200 plus 2, giving again 15,352, the result we had by applying directly the formula for the sum of an arithmetic series. In our next example, the question says find n, given that summation from r equals 1 to n of 5 minus 2r equals negative 165. This is a GC equation. The first thing would be to write the first term, the last term, and then the number of terms. The first term occurs when r equals 1, which gives 3. The last term would be when r equals n, and when you substitute n in the summand, you have 5 minus 2n, which gives the last term. And the number of terms again, upper limit minus lower limit plus 1. So we have n minus 1 plus 1, which gives n as the number of terms. Then we bring in the formula for the sum of the first n terms of an arithmetic series, which says the number of terms over 2 into the first term plus the last term. and this sum is supposed to be equal to 165. So we proceed to substitute our parameters, the number of terms n over 2 into the first term 3 plus the last term 5 minus 2n should be equal to the value of the sum, which is negative 165. When you simplify, you would get n into 4 minus n equals negative 165, and upon simplification we get n squared minus 4n minus 165 equals 0, which is a quadratic equation in n. And factorizing, we have n minus 15 into n plus 11 equals 0, which gives the values of n as 15 or negative 11. But we have to note that in sigma notation, the upper limit is always greater than or equal to the lower limit. So n being greater than or equal to 1, we have that the value of n then is 15. In the case of a geometric series, you would recognize that a series written in sigma notation is a geometric series when the argument or the summand of your notation is an exponential function, usually of the form ar to the n minus 1 or any other exponent. We recall that for a geometric progression with first term a and common ratio r, the general term is given by un equals ar to the n minus 1. We have to note again how to write the formula generally in words, in order that when the number of terms is not n, we will not be confused. The nth term, which preferably we should call the last term for a geometric series, should be the first term times the common ratio raised to the power the number of terms minus 1. Then for the sum of the first n terms, we have two formulae. There is first the formula for the sum of the first n terms, or the nth partial sum, which is Sn equals a into r to the n minus 1 all over r minus 1. And it occurs for the case where the absolute value of r is greater than 1. We also have Sn equals a into 1 minus r to the n all over 1 minus r, where the absolute value of r is less than 1. So in order to find the sum of a geometric series, the first thing you would have to do is to find the common ratio. It is the value of the common ratio that tells you which formula for the nth partial sum you are using. So once your r is an improper fraction, that means the numerator is greater than the denominator, be it positive or negative, you are using this other formula. And when it is a proper fraction, where the numerator is smaller than the denominator, be it negative or positive, you are using this other formula. There is also the formula for an infinite geometric series that converges, and a geometric series would converge provided r lies between negative 1 and 1, or the absolute value of r is less than 1. And the formula for the limiting sum when it converges is given by sum to infinity equals a all over 1 minus r, which is actually obtained in this case where the absolute value of r is less than 1. The series will converge, and the formula is actually obtained by taking the limit as n tends to infinity of this partial sum. In such a case, since r is supposed to be a proper fraction, a fraction in which the numerator is smaller than the denominator, as n tends to infinity, the term r to the n would normally tend to 0, and so the formula will reduce to a all over 1 minus r. Now we proceed with the examples. Write the following series in sigma notation: 1 plus half plus 1/4 plus the rest of the terms plus the last term, which is 1 all over 256. Again, as we saw in the case of an arithmetic series, when a series is given for you to write in sigma notation, you need the lower limit, you need the upper limit, and you need the argument or the summand of your summation. You get the summand or the argument of your summation by finding the general term of your series. This series happens to be a geometric series because there is actually a common difference. The second term divided by the first gives half, and the third term divided by the second still gives half. So there is a common ratio. So we write the general term then as UR equals AR to the R minus 1. So the first term times the common ratio raised to the power the number of terms minus 1. The first term being 1 and the common ratio being half, we then have that the general term would be half to the power R minus 1. We need to calculate the lower limit, which occurs when the summand is equated to the first term. When you equate half to the R minus 1 to 1, we note that 1 is the same as half to the power 0. So R minus 1 should be equal to 0, which gives R as 1. So the lower limit of our summation would be 1. We also need the upper limit, which is obtained by equating the summand to the last term. The last term being 1 all over 256. We then have that the summand, which is half to the power R minus 1, equals 1 all over 256. 1 all over 256 is the same as half to the power 8. So that equating the powers, we get R minus 1 equals 8. So that R equals 9, which is the upper limit of our summation. We can then write the series as summation from R equals 1 to 9 of half raised to the power R minus 1. And it should be noted that this series can also be written as summation from R equals 0 to 8 of half to the power R. Now it's important to know how the alternative is obtained, because this could occur in multiple choice questions, and if the right key is not the first one, it would be the second one. Actually, to get the second one from the first, so you simply add 1 to the exponent of your argument and then subtract 1 from the lower limit and subtract 1 from the upper limit. In the next example, we have given that summation from R equals 1 to infinity of 3 into half to the power R minus 1. Find the sum of the terms after the 10th term. Again, to start, we have to write out the series in order to read especially the first term and the common ratio, since we are dealing with a geometric series. You can see the summand is an exponential function. The first term would then be 3, while the common ratio is 3 over 2 divided by 3, which gives half. 3 over 4 divided by 3 over 2 is confirmed to be half again, so the common ratio is half. So the first term is 3 and the common ratio is half. In order to find the sum of the terms after the 10th term, we would have to find the 10th partial sum, which is obtained from the formula Sn equals A into 1 minus R to the n all over 1 minus R, since the absolute value of R is half, less than 1. So the sum of the first 10 terms would then be 3 into 1 minus half to the power 10 all over 1 minus half, which gives 6 into 1 minus 1 all over 1024, giving 3069 all over 512. Next, we find the sum to infinity, which is given as the first term all over 1 minus the common ratio, giving 3 all over 1 minus half, which gives 6. Now the sum of the terms after the 10th term should then be the sum to infinity minus the sum of the first 10 terms. That is how we will get that sum, which gives 6 minus 3069 all over 512, giving 3 all over 512. So generally, for a convergent geometric series, the sum of the terms after the nth term is given by sum to infinity minus the nth partial sum, which gives a over 1 minus r, the sum to infinity, minus a into 1 minus r to the n all over 1 minus r, which simplifies to ar to the n all over 1 minus r. So if we apply that formula directly to our problem, we would have that sum to infinity minus S10 equals AR to the 10 all over 1 minus R, which gives 3 into half to the 10th all over 1 minus half, giving 3 into half to the power 9, which gives again the result that we had up. In our last example on geometric series, we have given summation from r equals 1 to infinity of a into 1/3 to the power r minus 1 equals 12. Find the value of a. This is another GC equation. So the first thing we would have to do again, since we have summation from r equals 1 to infinity and our summand is an exponential function, it means we are dealing with a geometric series. Since the upper limit is infinity, it means we are dealing with the sum to infinity of a geometric series. So the first thing we would have to do is to expand the series in order to get the first term and the common ratio. The first term will be when r equals 1. When you substitute r equals 1 in the summand, you get the first term as a. And when you substitute r equals 2 in the summand, you get the second term as a over 3. And proceeding to the third term, we would have it as a over 9. So the first term is u1 equals a, and the common ratio is a over 3 divided by a, which gives r as 1 over 3. We then proceed to use the formula for the sum to infinity of a geometric series, which is a all over 1 minus r, and that sum being 12, we then equate it to 12 to have a all over 1 minus the common ratio 1/3 equals 12. Upon cross multiplying, we have a to be 12 into 2 over 3, which gives a as 8. From here we proceed to alternating series, and we should note that a series that is alternating is simply one in which consecutive terms alternate between positive and negative signs. We have an example: summation from r equals 1 to infinity of negative 1 to the r of f of r, where f of r is greater than or equal to 0 for all values of r. So you would recognize an alternating series generally when you have negative 1 raised to the power r multiplied by another function, generally a function of r. So in this series, if we generate the terms, we have the first term when r equals 1, we have negative 1 to the 1 of f of 1, which would simply give negative f of 1. When r equals 2, we have negative 1 to the 2, which gives 1 times f of 2, which should give f of 2. So what we notice is that when r is an odd number, the term is negative, and when r is an even number, the term is positive. We also have this other case, summation from r equals 1 to infinity of negative 1 to the r plus 1. You can see again the role that negative 1 raised to a power is playing in generating the series that is alternating. We note that when the position of the term is odd, the term would be positive, and when the position is even, the term would be negative. At this point, you note that one strategy you can use in evaluating alternating series is by grouping the terms. Another important fact is that for a finite constant alternating series, the parity of the number of terms is helpful in evaluating the series. Generally, if you have an even number of terms, the terms will cancel out to give a sum of 0. And when you have an odd number of terms, the terms would cancel out to give a sum equal to the first term. We proceed with an example, summation from r equals 1 to 6 of 2 into negative 1 to the power r. So you can generate the terms. When r equals 1, you have 2 into negative 1 raised to the power 1, which gives negative 2. When r equals 2, you have 2 into negative 1 to the power 2, and negative 1 raised to the power 2 gives 1. 1 times 2 will give 2 as the second term. Now we have to write out alternating terms of 2 from a count of 1 to a count of 6. So there are 6 terms, and so we have negative 2 plus 2 minus 2 plus 2 minus 2 plus 2. And to evaluate the series now, we group consecutive terms to have negative 2 plus 2 plus negative 2 plus 2 plus negative 2 plus 2. Each of the pairs resolves to 0. So it gives 0 plus 0 plus 0, which is 0. In the next example, we have summation from r equals 1 to 6 of 7 into negative 1 to the r plus 1. The first term would be when r equals 1, and when r equals 1, negative 1 would be raised to the power 2, which will give 1, and 1 times 7 will give 7. When r equals 2, you would have negative 1 to the power 2 plus 1, which gives negative 1 to the power 3, and negative 1 to the power 3 is negative 1. Negative 1 times 7 gives negative 7, and so the second term is negative 7. So the terms will alternate again between positive and negative, and since there are 6 terms, we have 3 pairs of consecutive terms: 7 minus 7 plus 7 minus 7 plus 7 minus 7, which gives again 0. Now we consider the cases that have odd numbers of terms, like summation from r equals 0 to 6 of 5 into negative 1 to the r. You would have 5 minus 5 plus 5 minus 5 plus 5 minus 5 plus 5. There are 6 minus 0 plus 1 terms. So there are 7 terms in that series, and you group them again. You would have 5 minus 5 plus 5 minus 5 plus 5 minus 5, and the last term would be unpaired, and that last term actually corresponds to the first term. So the sum of this series would be 5. Another example before we make a general conclusion: summation from r equals 0 to 7 of 9 into negative 1 to the power r plus 1. When r is 0, you get the first term as negative 9, and when r is 1, you get the second term as 9. Again, the terms alternate between negative and positive until you have 8 terms, because summation from r equals 0 to 7, there are 8 terms: 7 minus 0 plus 1. So pair up again the terms. We have negative 9 plus 9, which gives 0, negative 9 plus 9, which gives 0, negative 9 plus 9, which gives 0, and then negative 9 plus 9, which gives 0. And the final result is still 0. From these examples, we have quite a good number of observations to make. And the first one is that generally, summation from r equals 1 to 2n of k into negative 1 raised to the power r is 0. So when the lower limit is 1 and the upper limit is an even number, it means you are dealing with an even number of terms, and the terms would pair up and cancel out to give a sum of 0. When you have summation from r equals 1 to the upper limit, which is an odd number, and you're dealing with an alternating constant series, the terms would cancel out to leave out the last term, which corresponds to the first term of the series. In the case where we have summation from r equals 0 to an even upper limit, you are instead going to be dealing with an odd number of terms, because 2n minus 0 plus 1 gives an odd number of terms, and instead in this case the terms would cancel out to leave out the last term, which usually corresponds to the first term. When you have summation from r equals 0 to an odd number at the upper limit, you would have to deal with an even number of terms, because the number of terms would be 2n plus 1 minus 0 plus 1, which would instead give an even number of terms, and in such a case the terms would cancel out to give a sum of 0. And to conclude, we look at the example: summation from r equals 1 to 2214. Now, when the lower limit is 1, the upper limit directly gives you the number of terms. So we have the number of terms as 2214, which is an even number. So the value of this constant alternating series will be 0. Since there is an even number of terms, they would pair up and subtract to cancel out. Summation from r equals 1 to 1177. Again, the lower limit being 1, it means the upper limit gives the number of terms directly, and since it is an odd number, it means the value of the sum would simply correspond to the first term, which is obtained by substituting r equals 1 in the summand to have 11 into negative 1 to the power 1, which gives negative 11. Summation from r equals 0 to 25,000 of 21 into negative 1 to the power r. Here, since the lower limit is 0, we would have the number of terms as the upper limit plus 1, which will now give 25,001 terms. And since the number of terms is odd, the value of the series would correspond to the first term, which is obtained when r equals 0, 21 into negative 1 to the power 0. Negative 1 to the power 0 being 1, the value of that sum would be 21. Summation from r equals 0 to 237, the number of terms would be the upper limit plus 1. So the upper limit minus the lower limit plus 1 would give 238, which is an even number. So for this constant alternating series with an even number of terms, the terms would pair up and cancel out to give a value of 0. We proceed to have an example which is actually a further mathematics question of the GCE, a multiple choice question which says summation from k equals 1 to 2n of negative 1 to the power k equals a infinity, b 1, c negative 1, and d 0. Now, since the lower limit is 1, it means the upper limit gives directly the number of terms, because again the number of terms has to be 2n minus 1 and then plus 1. It gives 2n, and 2n being an even number, we can then have that the terms of this constant series would pair up and cancel out to give a sum of 0. Hence the right key is D. Now, in the case of a finite non-constant alternating series, you have to be very careful and in fact strategic in order to evaluate the series, and the best practice is to pair the terms and simplify before using the appropriate formula to find the sum. We proceed with the first example. Evaluate summation from n equals 1 to 10 of n into negative 1 to the power n. This is a GCE question. So in order to evaluate, we need to write out the terms so that we can see the pattern that the terms are following. When you write out the terms, you have first term, when n is 1, you get 1 into negative 1 to the power 1, which gives negative 1. The second term, when n equals 2, you have 2 into negative 1 to the power 2, which will give 2, and the terms would keep alternating from negative to positive. And here we can pair up consecutive terms up to the last two terms, so that we have negative 1 plus 1 plus negative 3 plus 4 plus the rest of the pairs, and then plus the last pair, which is negative 9 plus 10. In each of the pairs, you can notice that the sum gives 1. 2 minus 1 would be 1. 4 minus 3 would be 1, and the rest of the pairs would be given 1 up to the last pair, which is 10 minus 9, which also gives 1. Since there were 10 terms, 10 minus 1 plus 1 gives 10 terms. So since there are 10 terms, when you pair them up, you would have 5 pairs. Each of the pairs gives a sum of 1. So this series would be obtained by simply summing 1 5 times, which is equal to 5 times 1, and the result is then 5. Now, in the alternative method, we can instead group the terms into those that are negative and those that are positive. In the first group of terms, we have an arithmetic progression of 5 terms, and the first term is negative 1, while the last term is negative 9. And in the second group, there are 5 terms, with the first term 2 and the last term 10. So we can apply to each of the groups the sum of the first n terms of an arithmetic series. So we'll have the number of terms in this first group, which is 5/2, into the first term, which is -1, plus the last term, which is -9, plus the sum of the next series, which is also an arithmetic series. The number of terms being 5, we have 5/2 into the first term 2 plus the last term 10, and that gives -25 plus 30, giving again 5, the result we had above. Another example, evaluate summation from r equals 1 to 40 of r squared into -1 to the power r. So again, we write out the terms of the series, summation from r equals 1 to 40 of r squared into -1 to the power r. When r equals 1, we get the first term, which will be 1 squared into -1 to the power 1, which will simply be -1 squared. And when r equals 2, we'll have 2 squared into -1 to the power 2, which will give plus 2 squared. And you can see the terms will be alternating in such a way that the odd positions are negative and the even positions are positive, up to -37 squared plus 38 squared minus 39 squared plus 40 squared, which is the last term. Here again, the strategy is to group the terms and then see how they simplify. So we are going to be grouping consecutive terms, so the first 2 terms, the next 2 terms, and so on up to the last 2 terms. When you observe carefully, you see that each pair of terms forms the difference of 2 squares. In the first pair, we have 2 squared minus 1 squared. In the next pair, we have 4 squared minus 3 squared. And in the last pair, we have 40 squared minus 39 squared. So each of the pairs forms the difference of 2 squares. If we then apply the formula for difference of 2 squares, in the first pair we would have 2 minus 1 into 2 plus 1. In the next pair we have 4 minus 3 into 4 plus 3, and so on up to the last but one pair, which is 38 minus 37 into 38 plus 37, plus the last pair, which simplifies to 40 minus 39 into 40 plus 39. And you observe, you notice that the first of each factor in each pair would reduce to 1. So 2 minus 1 will give 1, 4 minus 1 will give 1, 38 minus 37 will give 1, 40 minus 39 will give 1. So that the series reduces to 3 plus 7 plus 11 plus 15 plus the other terms plus 75 plus 79. And you can notice that this is an arithmetic series in which the common difference is 4. 3 plus 4 gives 7, 7 plus 4 gives 11, 11 plus 4 gives 15. So this is an arithmetic series with the first term being 3 and the last term being 79. So to evaluate this series, we need the first term already, which is 3, the last term, which is 79, and we need the number of terms. Remember, we had 40 terms in that series. Summation from r equals 1 to 40 should give 40 minus 1 plus 1, which gives 40 terms. When you pair up 40 terms, then you divide 40 by 2 to have the number of pairs. It means after pairing 40 terms, we are left with 20 pairs. So these pairings simplify to give you 20 terms. This simply means this arithmetic series has 20 terms. An alternative to getting the number of terms, which is 20, is to use the last term and use the formula for the last term of an arithmetic progression, which will be a into n minus 1d, equating it to 79, and substituting a and d, you can still have your number of terms n equals 20. But it is simple to just obtain it from the original number of terms in the series, which was 40, and then we had to pair up the terms. Pairing up means we are dividing by 2, would end up with 20 pairs, which simplify to give 20 terms. So we proceed to write out the information. Since the sum is an arithmetic series with the number of terms n being 20 and the first term being 3, the last term is 79. We then use the formula for the sum of the first n terms of an arithmetic series, which says the number of terms over 2 into the first term plus the last term, giving the sum of the first 20 terms that we're seeking to find as 20 over 2 into 3 plus 79, which gives 820. Hence, summation from r equals 1 to 40 of r squared into negative 1 to the power r equals 820.